moving to our next speaker, to Aleksandra Zarzycka. So please join me here. And we will hear about experiences from the Netherlands as it comes to, again, some inspirations for next steps for Polish energy transition in the built environment. Aleksandra is working as a consultant for energy transition in the built environment at Royal HaskoningDHV. And she has a technical background in environmental engineering and building physics and services. And in her work, she helps organizations reduce the carbon footprint in their assets, supports the design of sustainable buildings, and develops strategies for almost energy neutral portfolios and neighborhoods. She's also an organizer of Energy Transition Academy within Royal HaskoningDHV, and a company-wide course covering all aspects of energy transition, not only the technical things, but also psychological implementations of the process. That's very impressive as well, and the floor is yours.
Thank you so much. Hi, everyone. In my presentation, I would like to actually cover 3 things. So I'd like to start with going back to the basics and showing you why the urgency for energy transition is there and where it's coming from. And then I would like to zoom in into one country, so Poland, to see how we're doing with energy transition, what still has to happen. And lastly, to an industry that is responsible for 40% of CO2 emissions globally, built environment, to show you some good practices from the Netherlands and how they can be lessons learned for Poland and for other countries. So I would like to just start with this image, which is showing greenhouse gas effects. So the energy from the sun gets reflected from the Earth's surface, and then it gets trapped by the layer of greenhouse gases in the atmosphere, causing it to warm up. So a couple of years ago, Donald Trump said that he doesn't believe that the Earth is warming. And actually he was right, because it is not the Earth that is warming, it is the atmosphere and the oceans. And there are multiple different greenhouse gases. We tend to talk about CO2 for simplification, so we can translate the effect of different gases to CO2 equivalent. All the policies are based on the reduction of CO2. So I was wondering, as a question to the audience, if anyone knows what is the concentration of CO2 in our atmosphere at this moment. So what is our starting point that we're trying to lower?
18.
A bit higher.
21.
In ppm, so it's 417 or 412 ppm, so parts per million. And you can see in this image that there are natural variations. So there are areas with lower CO2 concentrations, areas with higher, but they are not related to industrial sites. And if they are, then it's a coincidence, because this image mostly shows weather patterns. And it also shows that CO2 is a global problem. So if one country emits more, it doesn't stay above that country, it gets mixed into the whole system. So it's a problem that we have to tackle globally. And you can also see the historic levels of CO2. So they have been changing between 170 and 300 for as long as we were able to estimate that. So first of all, you can see we're out of scale. And second of all, from this image, you can see the direct correlation between the levels of CO2 and the temperature. So increase of CO2 is directly related to an increase in average temperature. And on this image, you can see that the scale of the increase of the CO2 concentration is unprecedented. It's happening so fast. So in 100 years, this peak at the end of the graph, this is something that has never happened before. So for that reason, in 2015, the leaders of all the countries came together in Paris to sign the Paris Agreement to promise to keep the increase of global temperature to first to 2 degrees, and then later was sharpened to 1.5 degree. And this is really critical because above this 1.5 degree, the impact on the, again, weather systems will be really significant. So that means more severe droughts, more severe rainfall, and yeah, disturbance to the systems that we actually rely on. And, when you think of 1.5 degree, maybe it doesn't seem so much, because if you think in summer we have around 24 and it's going to be 25.5, it seems like, okay, we can still continue living like this. But the implication of, actually you will see from this graph, this, maybe I should have a pointer, but okay, this dot here is 2 degrees change compared to the stabilized situation that we have here. So this is the temperature now throughout history. And we're hearing this argument very often that, well, the temperature has been higher and it has been lower and it's natural. And indeed, it has been 14 degrees higher and it has been 6 degrees lower. But what is interesting is that the last 10,000 years, it stabilized. And it also happens to be the time where the civilization began to grow. So we as humans were able to develop and to actually grow and flourish because of the stable temperature. So we need that to do more than just survive from day to day. So this stable temperature, if this gets out of balance, and you can see 2 degrees is significantly out of balance, that might cause a disturbance, and then nobody can predict what will actually happen further with the fluctuation. So we were lucky that this happened, and we're trying now to keep it like this. So there is the urgency. There is a need to limit the CO2 emissions. And the challenge is enormous. You can see Poland is the second country on the list. Netherlands is the third. So the dependence on fossil fuels is very, very high. The red color is oil, the gray is natural gas, and the brown is coal. And yeah, all the rest colors are renewable sources. So this is from 2018. It's a little bit better now. So we shifted a little bit left, but there is a very high dependency on fossil fuels. So for that reason, countries, Poland, have set ambitions to how far do we have to go until 2040 with the PEP, so the Polish energy policy, and how we would like our energy mix to look like. So you can see 15% will come from nuclear energy. We're all hearing about the plans for the first Polish nuclear power in the north of the country. So location has been selected. There were already first deals signed with the American technology provider. So the plan is that in 2033, the plant will become operational, and then every 2 to 3 years, subsequent units until the capacity of 6 to 9 gigawatts is reached, which actually is also here. So 6 to 9 gigawatts of nuclear energy. We also plan to have 16 gigawatts of solar energy by 2040. And with this one, actually, we're doing really, really good. Poland is one of the fastest growing markets for solar panel, especially in prosumer energy. This is due to the governmental backed programs such as My Electricity, Mój Prąd. So we're actually 10 years ahead of schedule. So the amount of installed power on solar power is now 10 years ahead of what was expected. So that's going really great. Well, we just had a great presentation about offshore and onshore wind. Huge potential on the Baltic Sea, estimated at 90 gigawatts, out of which 28 gigawatts on the Polish territory. So yeah, we're really hopefully going to, I think there are now deals to reach 5.9 gigawatts in 2027, and up to plans for another 11 in 2040. So yeah, that's going great. And then onshore wind, the discussion about the 10H rule, so that is a bit falling behind expectations. So I didn't put it here. I didn't have time to explain the whole rule, so I left it out. But there's only a certain amount of energy that we can generate in a renewable way. So the step number 1, which was already mentioned before, is the energy efficiency. We need to lower the need for energy and the amount that we need. And this is a very nice example from the Netherlands, how this was implemented for one industry, so built environment, by Dutch Green Building Council. So they estimated the available amount of renewable energy in 2050 that will be available for built environment, and said, okay, so now if every building uses below a certain threshold of energy, so kilowatt hours per square meter, then an entire industry is able to run on renewable energy and therefore comply with Paris agreements. So it's natural that, a hospital needs more energy than an office. So that's why you see different functions, which are in Dutch, but just different building types. Like a restaurant can have 200 kilowatt hours per square meter, but an office can have 70. And this is a great example of very practical way of measuring for a building owner to see if he complies with Paris Agreement or not. However, this is just one side of the story, because this is operational carbon. So carbon that is emitted due to the use of electricity or gas that is being phased out, of course. And you can see in yellow, this is the chunk of the CO2 per year. But there's also a gigantic amount of CO2 emitted at the construction of the building and also the demolition at the end and throughout the lifespan of a building, some replacement and maintenance. So every material, everything that goes into those buildings, they also have a very high CO2 emission. So it is really important to not forget that part. So if you think about it as a sort of global budget of CO2 that we still have before we reach 1.5 degree warming, there's a certain value for the whole world, and then per country also based on the amount of people, and per industry. So in this case, they said, okay, 11% goes for the construction of the materials. So for every decision actually that we make, like choosing an insulation material, this is really important to keep in mind. So you can see PIR, which is a popular insulation material, has an emission of 151 kilograms of CO2 per cubic meter, but hemp, which is a bio-based material, is 7 times lower. So by implementing this embodied carbon, we make sure that we really are seeing the full picture. So energy transition is not just energy transition, it's also material transition. And the Dutch Green Building Council now is updating the rules that we saw, the kilowatt hours per square meter, to also include embodied carbon. And there's already 50 organizations that signed the intention declaration to comply with this. And there's more and more every month. So yeah, I would like to leave you with this image, and thank you for your attention.
That was very inspiring as well to see the whole energy thing from the building perspectives, and indeed we also kind of experience those things on a daily basis. I hear from all of the colleagues here as well that lower temperatures and trying to use less energy here and there, but it's also important to think about what our buildings build of. That's true. Any questions to Aleksandra? Yes, there is one, please.
So it's very detailed, and I was wondering, how do you really retrospect temperature houses? Well,
yeah, so I was also curious about it. I Googled it. They, for example, the air bubbles trapped in ice, for example, or somewhere, they can measure from the concentration of CO2 in those air bubbles. So in rocks and ice caps, that's the way.
So the graph you showed, it's the temperature inferred from CO2 levels.
Ah, you mean how we measure temperature? It's a very question for geologists. I'm not sure, actually. I was curious about the CO2 because I thought how they measure that.
So going to deeper elements of the earth, we can see how was the weather going on. I think this is the explanation. The weather we adopt. This is the higher scientific approach.
Well, those early times there were no biological life, so it was.
Okay, thank you.
I also have a quick question about the slide before. So you showed the companies. What industries do it?
Yeah, different.
Because I don't recall many of those logos. Just curious. No?
Yeah, they're all different. No, well, this is, for example, a bank. Maybe another is a Dutch bank. Arcadis is an engineering company. Constructors. Also, well, this is a producer of materials. Very famous. Amazon uses all their materials. Yeah, different. Also, building control. For example, this is an organization that controls in a smart way with the sensors and tries to make smart buildings. So, yeah, not just building industry, also financial. Yeah.
Oh, cool. Cool. Thank you very much.
Just one question. R&D director just lower the consumption of the energy every year and 10%. So how you see we can do it in the laboratories when we consume such energy for the equipment, everything. So how you see the sustainability of the laboratories?
Yeah, so indeed. So here we're talking about building related energy. So that's for heating, for cooling. really,
for
this is process
70% of energy.
Yes. So this is, we have measures, we know how to tackle that part. But then when it comes to processes in the laboratory, that's really process engineering. So that's, that's then not the field of building. We see it as two separate things. So process versus building. Then you need process engineers to really look into how we can optimize the process, how we can use different technologies.
Awesome, thank you so much. Another hot topic for lunch discussions.
Yes, but before